Alright, so now we're going to talk about what's called LU decomposition. Okay, and the goal, if you will, is the following. So I want to find a matrix let's call it B, such that B times the matrix A is U, which is upper triangular. Okay. So in some sense, what this matrix B is doing is that it is writing in matrix form the kind of elementary row operations one does in Gaussian elimination. So let me try to give you a sense as to what I mean by that. So let me recall the following. So if you look at Gaussian elimination, right, then what you're really doing, say I have a 4x4 matrix and I don't really care what the entries are. The x's just denote some possibly non-zero entries. All right, it could be 0, but it doesn't have to be, at least initially. Okay, so you start with matrix A, and then if you recall, what you're really doing is that you're taking some multiple of row 1 and adding it to, it's like rows 2, 3, or 4 with different multiples, so that this column below the diagonal gets zeroed out. Okay, so I'm going to write that transformation as a matrix B1 acting on A. So B1 is going to be applied to this in such a way that when I look at the matrix B1 times A, I have now something of the following form. Okay, so there are zeros on this first column below the diagonal. Okay, and then I'm going to do something similar. At the next stage, I'm going to multiply this matrix here by B2, and it's going to have the net effect of zeroing out now the second column below the diagonal. All right, so this is going to be 0, 0, and then this stuff, I don't know what happens. Okay, so this is 0 below the diagonal, this is 0 below the diagonal. And then these x's, I mean, you know, in the same spots could potentially be different values. That's not the point here. Okay, so this is B2 times B1 times A. And then you do that one more time now with some sort of B3. Okay, and that's going to give you something now which is upper triangular, because it's going to zero out the third column below the diagonal, which is just this entry here, right? And as you probably know already, what you do is that in the first operation, you add an appropriate multiple of the first equation to the second equation, an appropriate multiple of the first equation to the third equation, an appropriate multiple of the first equation to the fourth equation, or the first row, if you will. All right, and then in the next step, these entries are already 0. You add an appropriate multiple of the second row to the third row, an appropriate multiple of the second row to the fourth row to zero out these two entries. And then in this step to here, you apply or you add an appropriate multiple of the first or the third row to the fourth row to zero out this entry. Okay, and then this is going to be what I call B3, B2, B1 acting on A, right? So the product of these things is what I call B, and then you have this A matrix, and this is going to give you an upper triangular matrix U, right? So that's operationally, it's like what's going to happen. So B1, B2, and B3, right, are matrices representing elementary row operations. Okay. And then I should make a remark that if you wanted to have matrices acting, sort of representing elementary column operations, instead of having the matrices multiply on the left, which is the case for row operations, you would have the matrices multiplying on the right for column operations. Okay, so so let me sort of write that as a remark. Multiplying A on the left corresponds to row operations on A, and then multiplying A on the right corresponds to column operations on A. Okay, all right. So that's an important observation to make, right? Don't drive yourself crazy trying to do elementary column operations by finding a matrix which acts on the left. It's just not going to happen. Okay. All right. So in order to do this, you just need to sort of briefly remember how to do matrix-matrix products. Right, so let me just briefly remind you of this. So recall matrix-matrix products. Okay, so if you have C is equal to A times B, right, so A could be a M by R matrix, B is a R by N matrix, and then C, which is the product, will be an M by N matrix. Okay, so I'm going to write this in the following way. So I'm going to think of A as a bunch of row vectors. I'm going to think of B as a bunch of column vectors. And modulo the fact that they are row or column vectors, the A's and the B's have the same length. They have length R, right? So A now has a bunch of M row vectors. Each row vector has length R. B viewed as a bunch of N column vectors. Each of these vectors again has length R. Okay? So yeah, so if you recall, then what you do is you do the same thing actually you do. It's like with matrix vector products, right? You take the row and you multiply it sort of term by term. It's like, you know, with the corresponding term in the column. Okay? And so in general, the entry Cij, right, is going to be this AI vector dot product with the Bj vector. Again, recall they have the same length. Okay, and so this is equal to the sum from k equals 1 to r of aik b kj. Okay, so that's what's happening. Right, so I'm not going to go into details. It's like this is stuff you should have seen before. Hopefully this is just a reminder. Okay, so anyway, what I had said before is that the reason why we're doing this is that we're going to try to interpret the elementary row operations which you see in Gaussian elimination in terms of a matrix B acting on A from the left. Okay, so let's see what's happening. So now back to Gaussian elimination. Okay, so, you know, in Gaussian elimination, I think of the rows as corresponding to equations, right? So each row corresponds to an equation, equation 1, equation 2, all the way up to equation n. And the row operations you have involve taking the first row and keeping it the way it is, Then the second row becomes E2 minus, say, A1, E1, right, and then all the way down to En, okay, minus An minus 1, E1, okay. And so the question is, how do I write this? So this is the map I want to apply, and how do I write this as a matrix multiplication? Okay. So you can check that if that's what you want to do to the matrix A in terms of elementary row operations, you can multiply the matrix A on the left by the following matrix. So you have ones along the diagonal, okay? And then on this column below the diagonal, you put down minus A1 all the way up to minus An minus 1. Let me just remove the box here. Okay, so minus A1 all the way up to minus An minus 1. The rest of them are zeros. Okay, so you have this multiplied by this matrix A is going to give you what I'm looking for, which is that the first row stays the same, the second row becomes E2 minus A1, E1, and then the last row is En minus An minus 1, E1. Okay, all right. So again, you can easily check this. So, all right. So now let's try to, look at Gaussian elimination of a 4x4 matrix, but then represent those operations in terms of these kind of linear transformations. Okay? All right. So let's see what happens. Okay, so let's look at an example. So you have A is this 4x4 matrix, 2, 1, 1, 0, 4, 3, 3, 1, 8, 7, 9, 5, 6, 7, 9, 8. Okay, so I want to do Gaussian elimination to zero out this first column below the below it's like the diagonal, right? So what I can write this as is the following. So I said you want a bunch of ones along the diagonals, zeros here, and then these entries you want to choose so that after the operation, right, that column entry, those entries here are 0, right? So I want to add 2 times equation 1, or minus 2 times equation 1, right, to this 4 here to zero it out. So there's a minus 2 here. Okay, and minus 4 times equation 2 added to the third row will zero out the 8. And then, so more or less what you do is you take that coefficient 6, you divide it by this entry 2, and you put a minus sign to that. So that's a minus 3. Okay, so that's the matrix B1 multiplied by this original matrix 2, 1, 1, 0, 4, 3, 3, 1. 8, 7, 9, 5, 6, 7, 9, 8. Okay, so this is what I call B1. This is what I call A. Okay, so now you can multiply B1 by A, and that is going to give you the following matrix. 2, 1, 1, 0, 0, 1, 1, 1, 0, 3, 5, 5, 0, 4, 6, 8. Okay, and then now, as before, we want to take a multiple, an appropriate multiple of the second row, and add it to the third and fourth rows, so as to zero out the second column under the diagonal. All right, and so what's going to happen is that again, there's 1, 1, 1, 1, and then the entries you have to fill in are these two entries below in the second column below the diagonal. Okay, and the entries you get there are 3 divided by 1 with a minus sign, so there's a minus 3 here, a minus 3, and then 4 divided by 1 with a minus sign is a minus 4. Okay, so that's the operation you want to act on. Again, acting all right. So maybe I shouldn't say that they're equal to each other. All right. So yes. Okay, so this is mapped by B1 to this, right? And this product is equal to this, and then this is going to be mapped by a second set of elementary row operations to this times that, which is 2, 1, 1, 0, 0, 1, 1, 1, 0, 3, 5, 5, 0, 4, 6, 8. And that thing is equal to now 2, 1, 1, 0, 0, 1, 1, 1, 0, 3, sorry, not 0, 3, 0, 0, 2, 2, 0, 0, 2, 4. And again, we see that this is now zeroed out. Okay, and then what I want to do now is to zero out this entry. So then I again apply a transformation, right, which again consists of ones along the diagonals, and then I have to find an appropriate entry here, which is 2 divided by 2, so it's a 1, but with a minus sign, so that's a minus 1. And then I apply that to this matrix again, 2, 1, 1, 0, 0, 1, 1, 1, 0, 0, 2, 2, 0, 0, 2, 4, and run out of space, but let me just say that that is equal to now a upper triangular matrix. Okay, so that's going to be equal to 2, 1, 1, 0, 0, 1, 1, 1, 0, 0, 2, 2. And again, what, if you recall, we did was to subtract the second row, the third row from the fourth row, right? So that will be a 0, 2 minus 2 is 0, 4 minus 2 is 2. So that very last entry at the bottom is a 2. Okay, so that's 0, 0, 0, and a 2. Okay, so that's U. Okay, and then U, all right, so this thing here is B2 times B1A, right? So this is equal to B2, B1A. This is equal to B3, B2, B1A. So U is equal to B3, B2, B1 times A, and this is what I call the matrix B. Okay. All right. So now you can do something here. All right. So we have, okay, so let's see what's going on now. Okay. So eventually what I wanted was to write down A as a product of a lower triangular and upper triangular matrix. So where are we at right now? We're at this idea that B times A is equal to U. And each of these BIs are lower triangular, but we don't know what happens to when you multiply them, okay? And it's not quite what you want, right? What you really want is that you want to write A is equal to something like B inverse times U, and you want this B inverse, right, to be lower triangular. Okay, so let's see what happens. So it turns out that there's going to be some luck involved. Okay, so about what this B inverse looks like. So So a bit of luck is the following. So what is B inverse, right? So B inverse is going to be, by definition, this product B3, B2, B1 inverse. And you can check that that turns out to be this product. So B1 inverse, B2 inverse, B3 inverse. Okay, so it's the inverse of the products is the product of the inverses, but with the orders reversed. And it's easy to convince yourself that that's not too surprising if you think about it. Okay. All right. Because I mean, if you want to take the inverse of this, you first have to invert B3. So B3 inverse times B3 will be the identity. So you're left with B2, B1. So you have to multiply again on the left by B2 inverse, and then you have to multiply on the left by B1 inverse. So the fact that this is equal to this is not so surprising. Okay. What is interesting though is that B1 inverse, right, which is the inverse of this diagonal lower triangular matrix of this form, -2, -4, -3, inverse of this is a very simple expression. It really is sort of this same diagonal entry, but where the column below the the column below the diagonal is the same except with a different sign. Okay, so instead of -2, -4, -3, you get 2, 4, and 3. Okay. And the other thing which is nice is that, so that was B, okay, so let me just write down what B1, B2, and B3 were. So B1 was 1, 1, 1, 1, -2, -4, -3. B2 was 1, 1, 1, 1. And there's a -3, -4, and then B3 was 1, 1, 1, 1, and then there's entry here which is a -1. Okay, so what is interesting is that when I compute this, right, B1 inverse, B2 inverse, B3 inverse, and multiply them all together, right, I have 1, 1, 1, 1, 2, 4, 3 coming from the B1 term, 3, 4 coming from the B2 term, 3, 4, and a 1 coming from the B3 term, right? So somehow it's like all those columns, all those terms below the diagonal which you have there, I just have to put them all into this lower triangular matrix, but with the signs changed, okay, for the entries below the diagonal. Okay, so that's nice, right? And so that's actually going to be my lower triangular matrix L. So now I have the following thing. So I have this matrix A, and I can write this as L times U, where A, as we looked at before, was 2, 1, 1, 0, 4, 3, 3, 1, 8, 7, 9, 5, 6, 7, 9, 8. So this is the matrix A, which is dense in some sense, in the sense that most of the entries are not 0. Okay, and then I can write this as a lower triangular matrix with 1s along the diagonals, 2, 4, 3, 3, 4, and 1. Again, all these entries just come from these B1s, B2s, and B3s, which represent the elementary row operations you needed to do Gaussian elimination. Okay, and then the upper triangular part is the Gaussian elimination stuff, right? The output of the Gaussian elimination, 2, 1, 1, 0, 1, 1, 1, 2, 2, and 2. So this is upper triangular, this is lower triangular. And then this is upper triangular. All right. So that's really very nice. And then we can do this in a little bit more generality now. So actually, let me just stop here for now. It's like, and then I will talk about how it does in a little bit more generality.